Okay, so we had left off in the last video with definitions of a sum of two vectors as well as scalar multiplication. And we talked about the meaning of those operations both geometrically and I guess you could say algebraically if you think about what's happening to them in their component forms. So continuing on in that vein, some terminology here. We say that two vectors are parallel if they have either the same or opposite direction. And you can kind of see up here why we would use that terminology for that. These three vectors here all have the same direction. These two vectors here have the opposite direction as these. But if we put a line, well, if we were to put lines through all five of these, all five of those lines would appear to be parallel to each other. So that's the terminology that we're going to use. Two vectors are parallel if they have the same or opposite directions. Okay, another way of saying that though is two vectors are parallel if and only if one of the vectors is a scalar multiple of the other, because that's how you get vectors that are the same or opposite direction as a given vector v, which gives us a very simple way to check for that parallel property. However, that scalar k has to be non-zero. Now, if a vector v is multiplied by the scalar -1, as we saw up above, then you get a vector with the same dimension, or sorry, the same direction as v, but the opposite direction. And we actually just call that vector the opposite or additive inverse of v. And rather than write -1 times v, we generally just write -v for that. Okay, so this will represent the vector in the opposite direction, but same magnitude as v. Having defined this now, we can think of subtraction as adding by an opposite. So what I mean by that is if we have two vectors, u and v, and we want to subtract those two vectors, u minus v, then we can think of that in a manner that you could also think of real number subtraction. It means the same thing as u plus the opposite of v. You can talk about subtraction of real numbers as one number plus the opposite of another number. So how do we interpret this geometrically? What does that look like? Well, so here's our vector u and here's our vector v, just a couple arbitrary vectors. If this is v, then -v is going to look like this. It's going to point in the opposite direction as v, but have the same magnitude. Okay, so u minus v is literally a sum of u with -v. And creating that parallelogram, using our parallelogram law, we would get this vector right here. Now, if I were to take vector v and move it down so that it coincided with this edge of this parallelogram, even though it would be pointing in the opposite direction as -v, it would still have the same length, so it could act as that side of the parallelogram. If I also took vector u and moved it down here, it could form the bottom edge of that parallelogram. And so one way of thinking of the difference between u and v, if you use this diagram as a guide, is if you take the vectors u and v and give them the same initial point. So notice now u and v have the same initial point. It can be interpreted as the vector that has the terminal point of v as its initial point and the terminal point of u as its terminal point. So it points in the direction of the first vector in this difference. This is useful because it naturally creates a triangle. And as we're going to see later, we can use properties of triangles with this kind of an arrangement. Okay? All right. So we've talked about addition, scalar multiplication, and subtraction now. So it's worth asking what it might mean to add or subtract several vectors all at once. And we use the associative property with vector addition. We can see from this diagram here actually that the associative property would work. So let's think about this for a moment. What does it mean to do u plus v plus w? Well, it can mean one of two things. It means I could be adding u and v first, followed by w, or it could mean I'm doing v plus w, getting a sum here, and then doing u plus that sum. But if the associative law holds for addition of vectors, then it shouldn't matter which of these we use, we should still end up with the same result. So let's take a look at the right-hand side of this first and see what it would look like in this diagram. Here's u and v. So the sum of u and v would be this vector right here, because they're already arranged in that form. Now if I take my sum, u plus v, and I add the vector w to it, then I go tip to tail, and the result should be the vector joining this initial point to this terminal point. It would look like this. So that's what the label down here means, u plus v plus w. What if I go the other order though? What if I add v plus w first, which would, if you notice, v and w are already arranged tip to tail, so that would mean that this is the sum of v plus w. And then if I do u plus v plus w, well, tip to tail, I still get the same vector. So geometrically, we can see why the associative property works. And the benefit of the associative property is that in practice, we can just drop the parentheses altogether and just write, you know, u plus v plus w that way, and not have any confusion as to what that means. Okay, here's an example in three-dimensional space. If I want to add u plus v plus w, if u is pointing this direction, v is pointing this direction, and w, you can kind of picture that as pointing into the page a little bit. The sum of these three vectors is represented differently now because we are giving them the same initial point. See if you can convince yourself of why this is true. This shape right here is called a parallelepiped. It's a three-dimensional solid, all of whose faces are parallelograms. We'll talk about these at the end of chapter 3. The sum of those three vectors will end up being a diagonal using this initial point and the opposite point as its initial and terminal point. Okay? All right, let's do an example where we use some of these operations but in component form. So I'd like to take these three vectors and evaluate 2u minus v plus 4w. So I'm going to start by writing them in component form. 2u looks like 2 times this vector. Okay, plus v, so plus v was 0, 2, 5. And plus, oh, I'm sorry, it was minus v. Let me change that to a minus v. Plus 4w, 2, negative 1, 2. Okay? Just like with order of operations with real number arithmetic, we do scalar multiplication before any addition or subtraction. So I'm going to bring the 2 and the 4 in. Our rules for this say that you can just multiply each of these components by 2. 6, negative 2, negative 4. Now, subtraction literally means adding the opposite of this vector. So I can bring that negative in because we know that the opposite of a vector is the same as taking the opposite of its components. 0, negative 2, negative 5, and then plus, bring that 4 in, 8, negative 4, 8. Okay, now it's just component-wise addition. 6 plus 0 plus 8 is 14. Negative 2 plus negative 2 plus negative 4, it's negative 8. And then negative 4 plus negative 5 plus 8, that would be negative 1. And so that would be the component form of the vector I get from performing those operations. All just about as straightforward as you can possibly imagine it. Okay? All right. So up until this point, the vectors that we've been focusing on have been vectors in 2 space or 3 space. And the reason for that is because we can visualize those types of vectors. Vectors in 2 space have an easy representation in the plane. Vectors in 3 space have an easy to visualize representation in 3-dimensional space. But if you think about it, well, what is a vector really? I mean, a vector is just an ordered n tuple. In this case, an ordered triple, where we interpret these as components for that vector, displacements of some kind. There's no reason why I can't think of an ordered 4 tuple as a vector. You know, each of those 4 components can represent 4 different measurable quantities. Your book goes into different interpretations of vectors in, you know, with more than 3 components. The downside of working with a vector that has more than 3 components is it's not easy to visualize those. But we don't necessarily need to be able to do that to work with vectors in higher dimensional space. So we define Euclidean N space as the set of all vectors that have n components, and we think of those as the set of all ordered n tuples, which here's a general ordered n tuple. We've introduced this notation before, but here's a reminder. The set of all ordered n tuples, so n space, is written this way, r to the nth power, and we usually just read this as rn when you see that. Okay. Now in Euclidean N space, we define the 3 operations that we've already talked about, addition, subtraction, and scalar multiplication, the exact same way that we've defined them for 2 space and 3 space. Everything is done component-wise. And similar to that, we define equality between 2 vectors to be the same. 2 vectors are equal if they have the same components. And the 0 vector is defined in the same way as well. It's the ordered n tuple, all of whose components are 0. Okay, and all the same properties that we get for vectors in 2 space or 3 space, essentially, will hold in n space as well. So let's talk about some of those properties now. This theorem lists several properties, 8 of them, I believe. So if you have these 3 vectors, u, v, and w, and they're all vectors in Rn, so it doesn't matter what n is here, and if k and m are scalars, then these properties hold. I'm not going to go through these one by one, but you should see some familiar ones in there. The commutative property, for example, associative property, not just the existence, but the purpose of a 0 vector. Adding a 0 vector to any other vector gives you the vector that you started with, regardless of the order that you added in. So 0 functions as what we call an additive identity. Opposites and so on and so forth. So these are all really important properties, and keep these in mind because we're going to use this list of properties as well as a couple more to generalize what we mean when we talk about vectors once we get to chapter 4. Okay, we're going to find that there's several other systems that don't necessarily look the same as Rn, yet still satisfy these same properties, and we would like to think of those as vectors as well. But again, that's chapter 4 when we get to that part. So I'm going to prove one of these. Let's suppose we wanted to prove D, the fact that u plus the opposite of u is equal to 0. These proofs are super straightforward. What we do is we take any vectors that are shown to us in this property, and we give them a component form. So I say let u be this ordered n tuple, u1 through un. Then what does it mean to do u plus negative u? Well, literally, the way we defined it, the opposite of u is the same thing as the scalar -1 times u. So if I rewrote these vectors in component form, and then I performed that scalar multiplication, -1 times this, I get negative u1 through negative un. Addition is done component-wise. So this should look like u1 plus negative u1, which we know is the same as u1 minus u1, and so on and so forth. And because I'm simply subtracting each component from itself, I get nothing but zeros for my components here, meaning that the end result is the 0 vector. Nothing fancy there. It's as straightforward as you could possibly imagine a proof being, and pretty much all of these will follow similar steps. So we're just going to worry about proving one of them here. Okay. Another theorem concerning a couple more useful properties. So if v is a vector in Rn and k is any scalar, then the scalar 0 times the vector v will result in the 0 vector. It's important to note that this 0 is different from that one. This one is not bold while this one is. That means this is a scalar, that's a vector. 2 different objects. Similarly, if I multiply any 0 vector by a scalar k, I also get just the 0 vector. And then finally, if we multiply a vector v by the scalar -1, we get the opposite of v. In fact, this was a matter of definition for us, but it's just being stated here as a property. I'm not proving any of these because they're incredibly easy to prove following similar steps as above. You can see that if you put a vector in component form and multiply all of its components by 0, then all of those components will become zeros, and that's what the 0 vector is. So this is not even really worth spending time on. Okay, so back in chapter 1, we defined something called a linear combination. And the term linear combination may be one of the most important terms for our class. We're going to constantly be talking about linear combinations, especially once we get to chapter 4 onward. Now, when we defined it back in chapter 1, we were specifically talking about a linear combination of matrices. Here, we're talking about a linear combination of vectors. So if you have a set of vectors, v1 through vn, and if you have a set of scalars, same number of scalars as vectors, k1 through kn, then the expression k1v1 plus k2v2 plus so on and so forth is called a linear combination of the vectors in that original set. So in other words, a linear combination is a sum of these vectors after they've been scaled by something. Okay, really important term for our class, linear combination. So let's see. Yep, that's it for section 3.1, and we're going to go ahead and move on to section 3.2 in the next video.